I have this meme stored on my computer, as well as my class lectures, vacation photos, and videos of my kids. All of this is stored using microscopic magnets. But as this meme says, something is wrong with my magnet. Let's look at a normal magnet. Grab it, put it near a paperclip, and it'll pick up the paperclip. Now, if I heat up that magnet, the paperclip will fall. We can understand this behavior by noting that a magnet is made up of atoms. Each atom acts like a tiny magnet. We use arrows to represent these little magnets. When the arrows point in the same direction, the material is magnetic. But as it heats up, the atoms start wiggling around, the arrows point in all different directions, canceling each other out, making the entire material non-magnetic. This is how 90% of magnets behave. As they heat up, they lose their magnetic properties. But my magnet does just the opposite. The material I'm working with is iron rhodium. When it is cold, the arrows point opposite to each other. It's not magnetic. And then as it heats up, the system suddenly flips and the arrows point in the same direction. It becomes magnetic. This strange behavior can be seen down here. At low temperatures, iron rhodium has no magnetization. And then as the temperature increases, the system transitions to become magnetic. This behavior is quite strange, and it is not well understood why it happens. In my research, I created a model to understand this. I looked at the atoms close by each other. Let's call them neighbors. Typically, nearest neighbors, seen here in purple with respect to the star, are the only significant interactions. But in order to explain what was going on, I had to look at an additional, more complicated 32-term interaction involving the next nearest neighbors as well, seen in green. I took all of these ideas and more and put them into a mathematical calculation, leading to a 4,000-line computer code that takes into account the temperature, applied magnetic field, thickness of the material, and many more contributions. This model provides a physical description of iron rhodium and an insight as to why and how this transition happens. It can make predictions, such as what temperature the transition will happen at if we say make the material thinner. But why do I care to do this? This model will allow for other scientists and engineers to make use of iron rhodium in magnetic data storage. For example, the hard drive on your computer is made up of a magnetic material divided into tiny regions, each of which stores data. The smaller the regions, the more data we can fit. But currently, we can't make the regions smaller. Iron rhodium's ability to so easily manipulate its magnetic state will permit for smaller regions and a huge increase in data storage capacity. And my theoretical calculations gives the insight necessary to make these developments possible, allowing for phenomenal improvements in magnetic technology. Thank you.